techniques. And in this lecture, we will continue to discuss some manifold learning models and so on. Oh yeah, by the way, and today we'll start to talk about first algorithm, diffusion. So to connect the time series analysis to manifold learning, there will be something in between that we have to talk about. That is the graph model. Okay, we want to use the graph model to describe the data set. And it is actually quite general, not just for time series analysis. It can be applied to other high-dimensional data analysis, which we will discuss also in the middle of the lecture. So usually, I give a graph, and we use these three notations to denote V. Will denote the vertices, and suppose there are n data points. And we will have an E set, and the E describes the edges among data points. So what you can see is V, that's nodes. Okay, and the E, you can view it as a subset of a V times V. So this is H. Okay, and then you will have omega, that is we call affinity, that describes how similar two data points are inside the data set. So sometimes this W is called affinity function. And there are many classifications of graph models and so on. There are also several textbooks describe graph theory, graph model, and so on, but we will not go into details. And there are many classifications. For example, the most common, most important classifications that we will encounter in this lecture will be undirected and directed. Okay, and the graph is called undirected if Wij is Wji for all I and j. But if it is possible to find some pairs so that Wij is different from Wji, that is called directed graph. And this is an example. So this is a directed graph. You can see there are in total 1, 2, 3, 4, 5 nodes, and there are several edges and with directions. And this describes the relationship in between all the nodes. And if you connect all the nodes, then it's called complete graph. And this is not a complete graph. And the weight on the edge can be either 0, 1, or determined by some kernel or whatever, can be more complicated. So this is just an example to help you to visualize what a graph is. And actually you can see a lot of more complicated examples. If you go go online, and well, there's social networks, economic networks, biomedical networks. Well, there are so many networks or graphs online, and quite a lot of so-called big data focused on this kind of data set and how to describe things. We will not go into details of each of them, but we will use the similar idea and focus on manifold learning for time series. But the same ideas and the many algorithms can be borrowed and used in all these examples. Okay, now we have talked about graph model, but how do you generate a graph if the graph is not available? For example, in many real-world examples, you may see that you will just given n data points, like n points, you'll get xi in Rp, okay, and I is from 1 to n. Sometimes this is the given data. Okay, or even more generally, I may give you yi, which is in some metric major space. I from 1 to n. And I give you all these data sets, and I ask you to do an analysis. And what can you do, or what you can do? Okay, to build up a graph or affinity graph from those endpoints, usually the first step is you try to find neighbors. And then connect the neighbors. And how to determine the neighbors? You can just say, I forgot, I don't want to determine neighbors, I just use everything. So it's complete graph. You connect every pairs of points. Or you can use K nearest neighbors. What you do is you have some kind of metric notion. You know how to compare two points. And for every point, you just find the K nearest neighbors and you connect them. Or you can say, oh, we have a distance, so we will determine all the points inside the epsilon distance. And if a point is within epsilon distance, then I connect them. Okay, so you can use different approaches to determine the neighbors and connect the vertices. And how to construct the graph is actually very important in many analyses, but unfortunately, to my knowledge, there is no universal rule. Usually it depends on the application and you have to try and error. But no matter what, once you determine a way to construct the neighbors, the edges, then you get a graph. You have vertices, all the vertices comes from all the points, and then you have the edges. And once you have edges and the graph, now you can use, again, the available information to determine the affinities. You can say two points are close nearby, then, well, they are similar, right? But how similar is similarity? So you need to define it. And usually, what we do is we will take not only a matrix that is given, you take a kernel, or this matrix can also be designed or be given, and you take a kernel, and the kernel is usually a decaying function, a Gaussian function, with sufficiently regularity, and you have some bandwidth h. And what you do is you just say, hey, if two points are very, very has distance d, then you divide it by h and apply kernel k. And a very common example of kernel is Gaussian kernel, and h is the bandwidth, and the distance sometimes is L2 distance. Then what you can see from here is if 2 points L2 distance is very, very small, then their affinity is big. But if 2 points have very big L2 distance, then their affinity is small. And in general, how to choose h, the bandwidth, is very, very important. And later in the lecture, we will have a section specifically focusing on how to determine h. And in practice, usually what we do is we will choose maybe 15% percentile or 25% percentile of all pairwise distances. And there is a reason why we prefer to choose this number, and we will talk about this in a bit. And how to determine kernel and the metric? Well, there are many details that we have to discuss. For example, metric itself plays a very, very critical role. Usually the original metric may not be the ideal one. We need to design some new metric out of it. And how to do it? We will provide several examples later. In the end, we get an affinity graph. Then how to do the analysis? To do the analysis, we need to work with the computer. And a computer usually can only save a vector, a matrix, and so on, and sometimes a tensor. Then what can we do to interact with the computer of the information about affinity matrix and so on? So what we do is very simple. Suppose you have a graph, an affinity graph with n vertices. Then we just build up an n by n affinity matrix called W. And in this affinity matrix W, if there is an edge in between I and j, then we just put Wij in the ij's entry of the W matrix. Otherwise, we put 0. So that is the affinity matrix. Very simple by construction. And then we build up an n by n diagonal degree matrix so that the i's diagonal entry will just be the row sum of everything, the row sum of Wij. And then we build up something called transition matrix. That is D inverse W. And this is the row sum. Because this is row sum, so D inverse W, as you can see, the row of D inverse W will be summed up to 1. And if all Wij are positive, then D inverse W will be a non-negative matrix with all row summed up to 1. So that will give you a transition matrix or an idea of random walk or diffusion on the data set. And you can easily see this idea by expanding D inverse W, V as a vector, and evaluate it as ith entry. If you do an expansion, you will see this is what you have: summation Wij Vj divided by summation Wij. And if you focus on the middle part, you see this is sum up to 1. So this gives you a probability idea of how you distribute the major or the information in V. So that is the idea of random walk or diffusion. And we will use this idea again and again in this lecture to describe how the data is organized. And there are some terminologies and the types of graph Laplacian. For example, you can consider D minus W. This is an unnormalized graph Laplacian. You can consider I minus D inverse W. This is called normalized graph Laplacian. And you can see the relationship in between these two is you multiply by D inverse on the left-hand side, and you will get I minus D inverse W. And also you can symmetrize the normalized graph Laplacian by multiply by minus half on the left and the D minus half from the right-hand side. Okay, so there are several versions, and they are all related. And there are some very basic spectral properties of graph Laplacian. For example, you can easily calculate and show that the spectrum of W is bounded by 1. Because its row sum is 1, so L infinity norm of the W matrix is bounded by 1, and the spectral norm is bounded by all the norms. So that is very simple. You can get all the spectrum of the graph Laplacian, normalized graph Laplacian, and so on. And we have a quick recall of the definition called the positive function, positive definite function. So a continuous function is positive definite if you can consider any numbers of any complex number and so on, and you evaluate it. It is positive definite. It is a negative function. Then this is called the positive definite function. So you can view f as a function as a symmetric matrix or Hermitian matrix. Okay, and it turns out if you have this kind of continuous function f, and it's positive definite, then only if the function f is a Fourier transform of a finite positive major. This is Bochner's theory. And based on this Bochner's theory, actually what we can say is the graph Laplacian, if I give a graph Laplacian and the kernel is Gaussian function or a positive definite function as the kernel, then the spectrum of the D inverse W, this is D inverse W, the affinity matrix is actually bounded in 0 and 1. That is positive definite and upper bounded by 1. So we have several nice properties, and because of this bounded in between 0 and 1, I imagine that it will give us the good properties about diffusion. Okay. This is actually manifold learning algorithm, not model. This is algorithm, algorithm. So we'll start to talk about once we have graph model and we have some basic spectral ideas. Then let's talk about the first manifold learning algorithm. Okay, the first manifold learning algorithm we will talk is diffusion maps, which is directly related to eigenmaps, or you can view diffusion maps as a generalization of eigenmaps. You can see the number of citations. That is, very, very good, sweet number, right? And this is 2003. This is 2006. That is the topic before deep learning. So, okay. So the diffusion map is actually very simple. What you do is you have this. I kept using different notations. This K here is D inverse W. Okay, sometimes I use A. And here, this is the K matrix D inverse W, affinity matrix. And you can see that this matrix is similar to D minus half W, D minus half. Okay, and if the matrix is diagonalizable, or in this case it's symmetric, so everything is perfect, you can write as eigendecomposition. And why do I say be careful here? Because W is an affinity matrix, and if this affinity matrix is constructed using K and N, K-nearest neighbors, then W matrix itself may not be symmetric or even not diagonalizable. But if you use epsilon ball or complete graph, then W is symmetric and everything is perfect. But if you use K and N to construct the neighbors, then be careful, it may not be diagonalizable. Okay, but no matter what, you can show that asymptotically it will be. Then you have eigendecomposition. Okay, and you have the diffusion map. Is defined using all the eigenfunctions and the eigenvectors. All the eigenfunctions and the eigenvectors. Not really all. You use the Q eigenfunction. The top Q non-trivial eigenvectors. And the top one will be ignored because the top one is always 1. Because you see D inverse W times 1 is always 1. So the first eigenvalue of D inverse W is always 1. But this eigenvector is trivial, so it's not really useful. We do not really use it. Okay, so we only use starting from the second eigenvector up to Q plus 1. Okay, and what we do is for the ith point, for the ith data point, we map it into a Q-dimensional space, and we use all the eigenvalues and the eigenvectors ith entry. And this as a new point in the Q-dimensional vector, this is the embedded point on the right-hand side. And once we get an embedding, we can evaluate the L2 distance in between two embedded points, and that is called diffusion distance. This is called diffusion distance. And when time is zero, when time is positive, it's called diffusion map. When time is zero, that is called eigenmap. So you can see eigenmap actually just use the eigenvectors. We do not have using any diffusion properties, but diffusion map we do use diffusion property. And then it is related to some notion called another algorithm called commutative time. And that is something we will not discuss. And so far, this algorithm has rich support, theoretical support, starting from 1994 in GAFA, which tells you that you can use all eigenvectors and eigenfunctions of the Laplace Beltrami operator to achieve an almost isometric embedding to the L2 space, and there will be starting from there there will be a lot of algorithms that depends on that kind of spectral embedding ideas to achieve manifold learning results. And another main paper is this CPAN paper in 2016, which shows that you don't need to use all eigenvectors and eigenfunctions. You don't need to use all eigenfunctions and eigenvalues. You can use finite eigenfunctions and eigenvalues to achieve an almost isometric embedding. And there will be some spectral embedding theories recently developed, and some robustness to noise result using random matrix theory. And we will come into some of the topics later during the lecture, so that you know why this algorithm can work and how it works. And there are several open problems in this direction that need to be discussed and to be further developed. But before that, let's take a look at the physical intuition for this diffusion distance. Okay, and you can see there is a dumbbell-shaped point cloud. And I tell you, there are 2 points, A and B and C. And now, I want to evaluate the distance in between A and B and C. As you can see, the Euclidean distance of A and B and C, they are the same. The distances are the same. But if you pay attention to the diffusion distance in the sense of how difficult you can diffuse from B to A, and how difficult you can diffuse from B to C, then you can see that actually it is very easy for you to diffuse from B to C because there are so many different paths that you can do the diffusion. But if you want to diffuse from B to A, then sorry, there are not many paths that you can choose to diffuse from B to A. So the so-called distance, if you measure it using the idea of time, how much time you need to diffuse from one point to another, then you can see that from B to A, the diffusion is longer, but from B to C, the diffusion is shorter. And that is actually the idea of diffusion distance. It captures the geometric properties of the difficulties of diffusion so that it can provide kind of a robust way to determine the notion of distance, called diffusion distance. Okay, and that is really the main application of diffusion map and diffusion distance. Well, not really main, there are several others, but that is one of them. So there are several basic properties of diffusion distance on the graph model, not on the manifold model, but on the graph model. We haven't discussed manifold model. We'll come back to the manifold model later. First, you may ask, oh, is this really a distance? Is this really a distance? The answer is, well, it depends. For example, if all the eigenvalues are not zero, then dt is a distance function. But this is not guaranteed, isn't it, in general? And there is a relationship to diffusion. Okay, so we have a definition that's called probability cloud of one point I at time t is nothing but you just consider all the diffusion that is small I, and you raise to power t. Okay, then what you can see is, okay, in the end of the day, the diffusion distance is nothing but ai raised to power t minus aj minus t, and the L2 distance is weight 1 over d. So you can see this is the diffusion distance is directly related to the probability cloud L2 distance with weight. That is something you can quantify. So in general, you can also consider several other distances, and they can all be useful, and so on. Okay, and dimension reduction, that is actually the main plan of many manifold learning algorithms. They always say, oh, we can achieve dimension reduction and a nonlinear dimension reduction and so on. Then let's take a look and see if this is really true. And first, it is something realistic because all the eigenvalues, as we discussed before, they are positive or non-negative and bounded by 1. So if you take time, diffusion time, for example, 0.1, 1, and 5, you will see that all the eigenvalues, they will decay in this way. And you can show that the truncated diffusion distance, that comes from truncated diffusion map, which comes from nothing but you define a truncation number. Okay, that is, you truncate so that all the eigenvalues are sufficiently large. Okay, and you consider this truncated diffusion distance. Then the truncated diffusion distance has some kind of good properties that you can capture. So, which tells you that actually, if you define some kind of threshold and you have a lot of diffusion time, and you diffuse a lot for a long time, then you will only use the first few eigenvectors. But if you diffuse for a very short time, actually you will use many eigenvectors. And the eigenvectors, the more the eigenvectors you have, the more you can capture the local geometric behavior. So when diffusion time is short, actually you capture the geometry of the graph. If diffusion time is very long, actually you capture the topology of the graph. And this kind of diffusion time and the topology geometry relationship should remind you some kind of uncertainty principle, just like in Fourier transform, in Fourier series, Fourier transform, Fourier analysis, or something like in the index theory and so on. And we will come back to this relationship later when we discuss more theoretical results on the manifold model. The final slide is focusing on dimension reduction. So usually people say, oh, we can apply manifold learning algorithms to achieve dimension reduction or even visualization. And there are so many algorithms, for example, local linear embedding, ISO map, diffusion map, or T-SNE U-map, which are very popular nowadays. Is it really true? Let's think about Klein-Bartle, just Klein-Bartle. So you know Klein-Bartle is a very specific topological geometry. It is a two-dimensional surface, but it's a two-dimensional this two-dimensional surface is not orientable, and it can be embedded in three-dimensional space. It can only be embedded in an Euclidean space with dimension higher than 4. Okay, so what you do is actually you have you take a piece of square paper, you roll it, and you try to link it. But when you link it as a torus, you try to twist the orientation of one end, and then link it back to the other end, so that it generates another dimension of freedom. So that it's not really orientable, or you have to do this kind of to piece a hole and do the connection, which is in three-dimensional impossible without destroying the topology. And this is a Klein-Bartle realization in three-dimensional space. And if you now run diffusion map on Klein-Bartle data, and you embed it in three-dimensional space, this is what you get. This is something far away from Klein-Bartle. So what do you really see? You do not see Klein-Bartle, and you may make a wrong impression or make a wrong conclusion. Okay, so this is why trying to understand the theoretical foundation or limitation is so important when you analyze geometric most of the algorithms. Otherwise, you may claim or get wrong impression out of it. So data analysis cannot break the topological constraint. That is very important. And if you don't understand this basic notion, then you may run into some crazy conclusions. And this is a final slide. This is the final slide. So this is a limitation of topological preservation. So we know this trefoil knot, which is something embedded in three-dimensional space. And in this trefoil knot is a parameterization. And if you run diffusion map, no matter how you do it, you can only recover S1. You cannot recover the trefoil knot. Why? Because trefoil knot is diffeomorphic to the canonical S1. And the only difference is the exterior topologies are different. And because diffusion map, it only sees the intrinsic geometry. It doesn't see extrinsic geometry or extrinsic topology. So it cannot capture the knot structure. So in the end of the day, you can only reconstruct the diffeomorphic nature. So it has limitation. It cannot recover everything. And then what can you do about it? You need a new algorithm or different sets. Even PCA is better than diffusion map to recover trefoil knots. So why do we? Yeah, right. So we need to know that it's limitation before you can properly use the algorithm. Okay, so that is it for now.